you have a model, I mean, you can include other variables in your model, but then they cease to become auxiliary because they are in your model. So, I mean, the way to think about this theoretically, first you build your model. Well, okay, well, first you build your model, then you collect your data. I know that's not usually how it works, but then you collect your data, and then if you have missing data, then you can use that in your missing data. You use auxiliary variables in your missing data model. So now, if you want to change your model and include some variables that were in the missing data model, that's fine. So it's fine to change your model. Go ahead.
Question. I deal with data with non-normal distributions of populations, given visibilities, small populations. I'm always having to adjust techniques for what in your world is an incredibly small n. We get 50 kids, we are singing and dancing. So I already am pushing my limits with repeated measures and multiple sampling techniques to get enough power to do my model test. Does this add additional risk?
Yes. Risk, yeah.
Yeah,
power,
power.
It doesn't give you additional power, and it adds additional risk. Yeah. I mean, if you're pushing your limits already with the analysis you're doing with complete data, then adding some missing data treatments are going to push your limits even further. And I understand your problem because my dissertation is on the relationship between corruption and democratic performance, and I had 186 countries. So that's not a big N either. And the bottom line was, and it was a multi-level model too, that I did not find a single missing data treatment that converged, that I thought was appropriate enough that converged. So I ended up hacking something together that I still don't like. And then I'm thinking about actually going back, well, I don't know if I'm going to do it or not, but going back and reanalyzing something with MLN, because maybe now, with the additional support that's in MLN to make those estimation procedures work better, maybe I'll actually be able to estimate. But no, you're going to have problems imputing. Your imputation models might not work. If you're going to use direct estimation, which is what I'm going to start to talk about with the next slide, you're going to have even more problems. So I don't think I have any good news for you on this one. But there is no magic bullet to not having enough data.
What then are some of the risks of just doing a list-wise?
And the same.
You just
bias.
reduce that power.
Yeah, you're basically prone to sample selection bias, unless your data is missing completely at random, and then you're just getting a loss of power. But even if you use missing data techniques, it probably won't increase your power at all, unless your rate of missing information is very low, and your missing data is just so spread out in your data set that if you actually exclude the cases with any missing data, then you lose most of your sample, then you might actually gain some power. If your rate of missing information is low, and your loss of sample size due to list-wise deletion is high, then you might actually gain some power, but otherwise, you're probably not going to gain back any power. Does that answer it?
As well as it can.
Well, sorry, it's not good news. So,
That's my deal.
any other question?
Just one more time, the rate of missing information.
Yes.
Is that a rate because it's like the average per person, how much they're missing?
The rate of missing information is calculated through a formula that I never really deciphered, but it is not, I can tell you what it is not. It's not what percent of people have missing on this variable. It's more than that.
Okay.
It also takes into account what other people's values are, etc. So it's not rate of missing data, it's rate of missing information. How much information are you missing by missing these cases?
And it tells you then how many imputations you should do?
Yes, it can guide your, well, nobody tells you how many imputations you can do. They say you should at least do 5. And that produces sufficiently efficient estimates. So your standard errors won't be too inflated or biased. When your rate of missing information is really high, then you might want to increase the number of imputations, because that'll correct for high missing information. But I mean, the other problem is that when your rate of missing information is really high, oftentimes your model, your imputation model will not run. So that's the bigger problem, unfortunately. I was doing a project with Deandra Ori. We were imputing something crazy. I'll talk about it later. And he had 81% his rate of missing information. So I told him to do 50 imputations, because there's just no other way of dealing with this. And when it started running the imputation models, it was running and running and running and running, and 2 hours later it produced one imputation. So we were happy that it actually did it, and I told him to go home and let it run overnight and see how many it does in the next couple of days. So these are computationally intensive procedures, especially when your rate of missing information is very high. Go ahead.
Are there any sort of guidelines for what size of the data set you have to have?
Now, most of these procedures were developed for the census, so very, very large data sets. Now, it can work in smaller data sets, though the larger the better, I guess, is the guideline. And my experience, and I don't look for this in any of the literature, my experience is if it runs great, then you're probably okay using it. Some reviewer might actually say, well, that was too low. But I've seen nothing in the literature that says what's too low and what's too high. So my guide to that is, if it runs, if it actually produces the imputations, then it was probably okay to use. Unfortunately, whenever I had this problem, that I had a low sample size, it didn't produce the imputations. So we never converged. Anything else? Now, there's one more thing I want to talk about. I will give you the slideshow. I seriously thought about giving it to you beforehand, but then I figured out that it's probably better if you pay attention to me and not the slides, and you take notes on your own. It's sort of part of my teaching approach. So I will make the slideshow available. So it'll be on the SSP website. You can go there probably tomorrow, maybe. By tomorrow, we'll try to post it. So you can go through these things again. Now, that doesn't mean you should not be taking notes, because you should, because this is really just a very rough outline. But I will give these out. So later. Okay. Anything else? Okay, then I'm going to get into the direct estimation of missing data. Now, the direct estimation of missing data is not imputed. And there's a major difference, and then we're getting into two religions over here of if you did imputation and you get a reviewer like Mike Neal, you're not going to get your paper accepted, because he hates imputation. Ken Boland, another person who hates imputation. So there are people who are prominent names in the literature who hate imputation. They much prefer to see a procedure that is directly estimating, and then there's vice versa. Now, most of the time, when I talk to these people who are much smarter than me, and I ask them about these missing data methods, they all say, if you can, always use a direct estimation to make your life so much easier. And it's true. It is going to make your life so much easier. So, if you can, try to use a direct estimation. Now, there are two main estimators that can actually directly estimate models with missing data. One is the full information maximum likelihood, and the other is the Bayesian estimator. I've used both of them already. M+ has FIML built in. The Bayesian estimator, I found, well, ML has it for multi-level models, and Amos has it for structural equations models. And if you want to do it, you can probably use WinBugs. Learn how to program these models in Bayesian and then use WinBugs, and that'll do it for you. But that's not fun. I can tell you that's not a fun thing. I'm just learning right now. So how it works? Basically, if information is borrowed from the cases where information is available. So estimation-wise, that's how it works. It assumes that the missing cases follow the same multivariate distribution. If you think about maximum likelihood, you hear about multivariate distribution, multivariate normality, how it's very important. Basically, if you have a missing case, you already have a distribution. Looks like this for two variables, and there's a missing case over here, and you still know where that would lie in the distribution if there's some information available on it. Hopefully there's some information available on it. Now if you would have to assume that in a univariate distribution, you would have to assume missing completely at random, because then there would be no information where it would lie in the whole distribution. It would just one distribution, so just a univariate distribution. So the way this is calculated, now, once again, this is over your head, don't worry about it too much, it's the application that matters for you then, but I do want to talk about this a little bit for the people who are actually interested in the computation of it a little bit. Maximum likelihood is calculated for each pattern. That's how it works. They take each pattern, they pull them apart, and they calculate it separately for all patterns, and the contribution to the likelihood function is summed across these patterns. Now, one important thing, and now this is the default in most software, is that to be able to assume missing at random in this estimation, you have to use the observed information matrix, not the expected information matrix. If you use the expected information matrix, you can only assume missing completely at random. And I know most software now uses the observed information matrix for the estimation by default, but check on that. If you see something in the output that says it's expected information matrix, be very careful and find some setting there you can change that, because then you cannot assume missing at random. So if it converges, it works. So that's the bottom line for most people. Now the Bayesian procedure, it requires a prior distribution. Again, this is a problem because the way it works is it takes your prior, it does Bayesian updating based on the data you have, and then it produces a new distribution, and then it does that again. Takes the newly calculated distribution as the prior, does the Bayesian updating, and it produces another distribution, or another value, another estimate. So that's pretty much how it works theoretically. I don't know the exact math of it myself either. I worked through it once, but I don't want to ever see it again personally. That's kind of how it works, and it does that over and over again. And once it's gone through the cycle so many times, it's called its past the burning period, then you can actually just take randomly an estimate, and then you can let it run for another 1,000 cycles, and then take another estimate, and that's how you actually sample your imputations. So that's how the Bayesian works. And the solution is unbiased under missing at random mechanisms. Now there's some research, if you're interested in this, if you do Bayesian work, there's some research now that actually claims that your prior distribution will not influence your posterior distribution. They just come up with a method to do that, and it's a very fascinating article here, which is, I can send it to you. It's another small, very localized journal. I think it's one of the most groundbreaking things that happened to Bayesian statistics in a long time. It raises some problems again, but if it would work and it would be implemented, then the whole debate about the prior distribution as a problem could go away. So there's some exciting work in that. Unfortunately, it's not implemented in anything yet, so you'd have to do it by hand. You have to do the calculations by hand. Now, with direct estimation, there are some problems. You can have missing data on the dependent variable if you're doing a structural equation model on the endogenous variables. So that is not a problem. The problem comes when you want to do, when you have missing on an independent variable or the exogenous variable. Now, somebody asked earlier, so is it a problem if there's missing data on the auxiliary variables? Well, for imputation, it is not. You can still impute the model, because what you need to do is you need to specify all the variables that have missing on them and all the variables that don't have samples the imputations from that. Now with direct estimation, if you have all your exogenous variables, all your auxiliary variables will be exogenous variables or independent variables in the model once you try to include them, and I'll show you in a second how to do that. So missing data is more problematic. Now what you have to do is you have to take these variables and put them inside the model so that they're endogenous somehow. And there are ways of doing this. And if you know structural equations modeling, they'll make a lot of sense to you. If not, I'll just show you how to do it. So at least I hope. Now, so let's take a part of a structural equation model because this wouldn't be identified, it would be just identified. So you have x, which is an independent variable, predicting a dependent variable, y. Now, your independent variable is exogenous, so you cannot have missing data. Now, what if you have missing data on this independent variable? What can you do? Now, what you can do is you can create a latent variable that perfectly predicts this variable, and you can say that it has zero residual. That means you're creating a latent variable that has the same metric as the observed variable, and that observed variable has no error. So you're measuring it without error. So this latent variable is now an endogenous variable. The observed variable is not an endogenous variable because the latent variable is predicting it. So there's an error going into something predicting this variable. That's by definition a dependent variable in a model. And then you can take this latent variable and have this variable predict your y. And then both variables in your model are endogenous variables, so you can have missing data on both of them. And tomorrow in the full information maximum likelihood workshop, I'll show you how to do this at least in N+. Now, how do you include auxiliary variables? That's the question. And this is something that John Graham worked on in 2003. He published an article. It is, if you know structural equations modeling, it is really, really simple. It is so simple that when Greg Anders was teaching the structural equations modeling class here a couple of years ago in education psychology, he taught it in his intro to structural equations modeling class because it was so simple that we all understood it. It was not even near the end. I guess it was near the end of the term. So it is actually very simple. Now, all you need to do is you need to correlate your auxiliary variables with all your observed variables and all the residuals of your endogenous variables. Well, basically, you need to correlate the auxiliary variables with all your other variables. That's how you do it. So you build your model, you take all these auxiliary variables, you correlate them with each other, you correlate them with all the variables that are in your model, the independent variables and both the dependent variables, and you have a model where the auxiliary variables are corrected for. Now, everybody says, well, you're throwing a lot of variables in your model. Is that going to contribute to your model misfit? No, it won't. Because all those variables are fully saturated in the model. They do not contribute to the likelihood function at all. There's zero contribution. They're all correlated with everything else. So they do not contribute to misfit at all. So what does this look like? So, and these are actually correct slides. I should put that up there. Make that correction before we put it online. So for a regression model, this is what a regression model looks like in the structural equations modeling framework. Here's your dependent variable. Here's your two independent variables. You allow them to correlate. And you have an error term. You have a residual of the dependent variable. Now to include auxiliary variables in this model, all you need to do is take this variable, take this auxiliary variable, correlate it with the other auxiliary variable, take both auxiliary variables and correlate it with both of your independent variables, and then take the auxiliary variables and correlate it with the dependent variable, in which case you're correlating it with the residual of the dependent variable. How many of you know structural equations modeling in here? You're like more than 2 people? Okay, good. Because then at least it's making some sense to some people. And it's really that easy for regression. For a path model, same thing. You can have x1 predicting y1 and y1 predicting y2. Same thing. You just correlate the For a full structural model, same thing. You can have two factors measured by two variables each. One factor is predicting the other factor. There's a residual of this factor. And then you just take all the residuals of the observed variables, but not the latent variable. So you always have to take the observed variable. You take the residuals of the observed variables and the observed variables if it's an exogenous variable, but we don't have that in this model. And then you correlate it with each other and correlate it with the residuals. So this is how you include auxiliary variable in maximum likelihood model. It works for a whole array from a simple regression all the way to a complex structural equation model. Downside is that it's a good idea to be familiar with structural equation models when you want to do this. Any questions? Go ahead.
Yeah, so all those y's are the unit values? Or like
No, we're not doing any imputation. When you're directly estimating, you're not doing any imputation.
you specify the whole?
You're estimating the model with the missing data included. And you can do that with maximum likelihood estimates, and you can do that with Bayesian estimates. And here, you do not have to do any imputation. You do not have to fill in the data set. So basically, the downside of doing this is you have to use a different estimator, you have to use specialized software, you have to rebuild your models in a way that they fit this structural equation modeling framework or maximum likelihood modeling framework. The upside is that it's relatively simple. You don't have to do things 10 times. You don't have to combine results. So it just gives you estimates, and you can expect that they're unbiased under the missing at random assumption. And you can include auxiliary variables. For a long time, this was the big debate, that imputation is better because you can't include auxiliary variables. Well, you can include auxiliary variables if you're not imputing, if you're directly estimating. It just makes your model ugly. But in some software, it's pretty easy to do. Unfortunately, the only structural equation modeling software I use regularly is M+. It's really easy to do M+. So easy to do M+, that Joe Schaefer said that if it's really that easy, I should just write a note in structural equation modeling or one of those journals saying, hey, you guys should start doing this because nobody does this because it's ugly. Nobody does this. So just said, why don't you write a note in like a one-page article and say, hey, you guys should start doing this. It's so easy. And I'm working with Greg Enders actually on doing that, but we're actually going to include other software too and how to do this in other software. It's one of the projects I'm working on, making clear passage. Unfortunately, though, this workshop has been giving me the kick to think about these things again. And the more I read, the more I see how this is like important. So it's not hard to do if you're familiar with those softwares. Any other questions? Okay, so not missing at random situations. Well, this is a mess. It is really a mess. Really difficult situation to estimate. You have to make a lot of assumptions. There are three approaches to deal with this kind of data. One is including auxiliary variables that can predict the values of the missing data. So not the pattern, not the missingness. The missingness is just, is it missing or is it not missing? That's enough to satisfy the MAR assumption. If you can find auxiliary variables that can actually predict the values of the missing data, then you can start to alleviate data that is not missing at random. Unfortunately, as you know from most of the models you read in your lifetime, it's impossible to build models that predict perfectly. So, or it is possible, but those are not good models. So, it's impossible to completely alleviate all the bias that comes from data not missing at random. Though, if you can theoretically assume MAR, and you know that even if there is some NMAR data, NMAR missingness in there, you know that your values should be correlated with the auxiliary variables. You can even claim that, well, I can assume MAR. I made a good theoretical claim for it, but even if I'm wrong a little bit, I'm alleviating that bias by this. So you can actually make some claims that even if you have NMAR data, you're alleviating some of that bias, though it will never be perfect. To be able to model NMAR data perfectly, There are two approaches. There is the pattern approach, which basically models your model and the missingness simultaneously in a single model. And these models are messy. Models are really, really messy. Like you're used to modeling just your regression and not your regression together with the missingness. So you have to model two things at the same time. Or there's the mixture approach, which makes assumptions about your missing data. You have to make some assumptions about your missing data and how it is different from your non-missing data, and then you can, if those assumptions are correct, you can actually make good estimates. Unfortunately, the assumptions are not testable. So, the auxiliary variable approach. So we used auxiliary variables to satisfy the Mars assumption already. So we use auxiliary variables to predict missingness. But now, if we use auxiliary variables, the values, it'll leave a text. Kind of going through that again. Just wanted to emphasize that unfortunately all the bias will never be eliminated unless your auxiliary variables predict perfectly, which they won't. The pattern approach is based on something called the Heckman regression equation. Now, Heckman wrote this article back in the 70s, and it was quite groundbreaking. Yeah, it was a two-step approach that you didn't really model simultaneously. You modeled in two steps. But unfortunately, it did not work unless the model for your missingness was different than the model for your estimate, for actually what you're interested in. You have to have different models for the two. Now, today, it can be done simultaneously with something similar to structured equation modeling, but the estimation is really, really difficult. The surface of the likelihood is often flat, and that estimation is really, really difficult, though it is implemented in some software. I know that Stata has a byprobit command that does this, and about 4 other commands that does this. And there's some modules in R that will actually do this. So again, originally estimated in 2 steps, but to identify the model, the 2 models needed to be different. One that predicts your missingness and the one that predicts your dependent variable. Now you can model it jointly, and there's some quasi-likelihood approaches that actually overcome the computational difficulties. And from what I've seen, it actually works in Stata. I've seen a lot in Stata, it actually works. And you might be able to have missingness depending on the estimation procedure. As I said, I don't know much of the implementation of this, I just know how it works. I've only used this once. Fortunately, I didn't have this situation too often. It wasn't even my data then, it was somebody else's. But I believe that you can have some more missing data depending on how it's implemented. I mean, theoretically, you should be able to. I don't know about the implementation. Now, what is really of interest is the residuals of the 2 models you're estimating jointly. If you're estimating those 2 models separately, you're assuming that there is no correlation between the errors of the model that predicts your missingness, and there is no correlation between the error, the model that predicts your dependent variable. So you actually assume, if you're estimating separately, you assume that there's no correlation. Now the problem emerges, the NMAR missing data by definition emerges when your missingness is predicted by the values that are missing. So your residuals can carry some information of those values. Now, when you allow, this is why you have to estimate jointly, but when you allow your 2 residuals, the model that predicts missingness, and the model that predicts dependent variable, when you allow those things to correlate, your estimate will be corrected for the NMAR missing data, and they will be unbiased, assuming it converges, it works. approach, you basically assume that there are two distributions within your data. That's why it's a mixture. Mixtures are data with multiple distributions. One is what you observed, that is a distribution. And the other is what's missing, that is another distribution. Now, we don't know what the missing distribution looked like. We just know that it's different from the one we observed. Because it's not missing at random, we know it's different. Now, if you can make some good assumptions about how that distribution is different, then you can estimate n more missing data. So let me give you an example. Let's say you know that people who do not report their weight are people who are tend to be heavy or more weight. So let's say you can make the assumption that the people who have missing data are on average 10 pounds heavier than those who report their weight. The distributions are the same, only the mean of that distribution is different. So you just made some assumptions about your distribution. You just made the assumption about the mean of that distribution. Unfortunately, these assumptions are not testable. So you need to be a good enough expert to be able to make that judgment call and theoretically justify it that the people who do not report their weight are 10 pounds heavier. Now, when this approach is used, it's a really, really good idea in common practice to do some sensitivity analysis. What if you make different assumptions? What if you assume that it's not 10 but it's 15? Will that change your results? What if you make the assumption that it's 20? Will that change your results? Now, how do you do this? Very simple. You do imputation. You can do multiple imputation. You take all the values you imputed, and then you modify it based on your assumption. So in the previous example, what I would do is I would impute under the missing data model, that the best missing data model I can come up with, then I would take the imputed values and add them to all. And then I would run my analysis. And to do the sensitivity analysis, I would then go back and add 5 more to those people that I imputed. And then I would do the analysis. And if your results don't change, you have a better case than if your results change tremendously, because your assumption, again, is not testable. Okay, any questions about this before I move on? And it could be done with likelihood methods. It's just you have to basically program all that in yourself, because there are no prepackaged solutions. There are no prepackaged solutions, period, but it's relatively easy to do with multiple imputation. Okay, any questions? I mean, this is difficult stuff. Very few people do this. And it's probably a good idea, because I don't think it's good practice to do this, because there's so many assumptions you have to make, so much trouble to get into. So, but I just wanted you to know that there are these approaches out there. Okay, now I do want to tie this back to design a little bit. Like when you design your study, first of all, avoid missing data. Do everything you can to avoid missing data. When you cannot avoid or anticipate it, you should collect data that will predict the missingness. And if you think that you cannot satisfy that, then you should at least collect data that correlates the value of the missing values, because that will alleviate even some bias that comes from n-bar missing data. Examples, I already went through a couple of these. Income, you can ask them what kind of car they drive, how much money they plan to spend on vacation this year, how much money they spent last year. I just read a very good example in Joe Schaefer's paper on attrition, and this is getting into the longitudinal stuff that we'll talk about more on Monday. But let's say people are dropping out of your survey. one of the best ways to collect data that will make your data more missing is ask him, are you going to drop out? Ask him 3 questions. How likely are you to drop out from this? If, let's say on a drug study, how likely are you to drop out if the drugs work? You say, well, if it works, I might never come back. I'm healed. How likely are you to drop out if the drugs don't work? So will they keep trying? So that can actually alleviate the bias that can come from attrition. You can actually collect some data that will make your data more. Okay, I've gone through the theoretical part of what I plan to talk about. So if there's any questions, we can talk about them now. If you have anything you want to bring up. And from now on, I'm going to talk about some very interesting missing data problems, because missing data problems cannot just solve your conventional problems. Missing data problems can help you in your research design, can actually solve very unconventional problems. And there are a lot of statistical problems or research problems that you can think about as missing data problems. They'll help you, in a way, find a solution. So I wanted to bring out a couple of these that I had experience with or that I encountered. Some of them are stuff that there's absolutely no research on this. I just had an idea and I threw it out there, and I had a room full of people kind of nodding, thinking like, well, no one ever thought of that. But I just wanted to throw this out there to you with some examples. But if there's any question about the theoretical part, please ask now, because it's a good time to do it. Go ahead.
I'm working on a tricky situation of work where we are recruiting folks with only cell phones. So what we are trying to do is to recruit cell phone only people for a study. And when we call them, and we have a very strict guideline saying if they are driving, and when we call them, we are not supposed to talk to them, or I guess we have to tell them that we will call back or something like that.
Okay.
So that's kind of just for liability sake. You don't want to get into that of all the liability issues. So what's happening is the people whom we call them, and even though they say it's okay, I can talk to you, I can be part of the survey now, it's okay, but they still say no, we'll call you back. So what we are seeing is when they say they're going to call back, or when we try to reach them, we find a lot of people missing. I mean, we cannot reach them. They aren't able to take the survey the first attempt when we call them, use their writing. But for some reason, when we are trying to reach them for a second time, or even 3 or 4 callbacks, we are not able to reach them. I'm just wondering, what is the auxiliary variable that you would recommend that they do?
Well, since you cannot collect any auxiliary variable because you have no opportunity to ask questions, I can't recommend anything. If you can ask one question, ask them how many hours a day they drive. Because that's the best variable that will predict if they'll be missing because they were driving when you called. So, I mean, if they're willing to, it's live and it's a legal question. If they're willing to ask one question, that's what I would ask.
The thing is, we start off asking the first question is, are you driving right now? So
Yes.
That's the very first question.
And if they say yes, are you willing to ask one more question to improve your data before you hang up is the question. And if you cannot collect any data, then I cannot tell you what auxiliary variable is like because you cannot collect any. But if you are willing to collect data even under those circumstances, that's what I would ask. How many hours a day do you drive on average? That would be the best predictor of will they be driving when you call. And that can actually be worked into the sampling list, because I don't know much about it. It was always the area I hated in survey research, but there are a lot of people around you that just know that stuff really, really well. So, and that can be treated as good enough response. It's a good weighting techniques. Anything else? examples. This will be fun. This won't be as rough. And feel free to ask questions. This can be more interactive now. So let's talk about latent variable models. What are latent variable models? Latent variable model is a missing data problem. When you have a latent variable, that's variable you don't have information on. That's a variable you don't have. That's why it's latent. You don't have it. So if you think about the latent variable, this is the pattern that you're dealing with. You have 3 observed variables. You're assuming, maybe you have one missing variable, and just given that these 4 variables, you have more missing data that are all the variables are missing on the latent variable. That's your pattern. That is a latent variable model. And the solutions computationally are not that different than some of the solutions we talked about. So when you're estimating with maximum likelihood, you're estimating a latent variable model, you're dealing with a missing data problem. Now this is just an example to get you to think outside of the box. Most of you have seen latent variables. I hope it's a missing data problem. You don't have data on that latent variable. Okay, missing by design. I've gotten a lot of questions already about this one. Missing by design is when you put missing data in your study. Why the hell would you want to do that? Maybe you should ask Gary what he wants to do it, because I know he wants to do something like that. Well, let's give you an example. I have 120 questions. If I give 120 questions to anybody, you can ask the survey people what they'll tell you. They'll tell you to go somewhere. You're doing research on kids. What if you want to collect data on kids? Can you ask 120 questions? No, you can't. There's survey fatigue. In these situations, putting some missing data in your data set might not be a bad idea. You can only ask, let's say, half of the 120 questions. That's 60. You might actually be able to pull that out in a survey. Probably 120 might be too much, but 60 you might be able to do. So what you do, you put missing data, randomly, you put missing data in your survey. And then just analyze it as with the missing data techniques we already talked about. It is missing completely at random, so you don't need to deal with auxiliary variables. The analytical techniques we discussed work in this situation, and they are unbiased. You're losing power. That's the one thing you're losing. You're losing power. But it might not be a bad idea to do this. Now, what other situations would you want to do this? Now, you might want to do this when you're paying the respondents by the question. You might want to decrease your costs. You want to collect a lot of information. You don't mind losing a little power just to decrease your costs. This might be a good way to do it. Context effect. I was sitting in Bob Belly's wonderful class on survey psychology. It was a great class, by the way. It was one of those classes that I was sitting in there thinking that I'm getting a lesson in common sense again. Because that's what survey research is. You sit there and they tell you a lot of things that makes perfect sense. But you would never think of them on your own. So, once you listen to a lot of that, you become an expert in surveys, but it's all common sense. At least that's how I felt. So I was sitting in that class thinking, oh my God, I can't believe I'm listening to this. I'm more of a stats guy, I'm more of a numbers guy, so that class in the survey field is really not a numbers class. And they talked about something called context effects. And I was sitting there, and I thought, oh, maybe I can solve this one, and I'll go into detail on that a little bit later. Yeah. And I did solve it as a missing data problem. I just presented a paper on it in Prague a couple months ago. So how do you do this? Well, you randomize what will be missing, so it's missing completely at random, and you analyze the results and discuss the methods. So, what are we doing? Actually, Gary over here had a grad student who I just met in Budapest a couple of weeks ago, and we were talking about doing research on a cognitive task. And what we're going to do is we're going to put faces like this one on the screen, and you need to figure out if this person is playful, comforting, irritated, or bored. Or the person, the respondent, will have to figure this out. It is sort of a test of how well you can read other to do with how much empathy the person will have. He does his dissertation in political science on empathy. And now we want to take a look at this. Now, what's our problem? Our problem is that the funding agency we want to go to is an economic funding agency. They do behavioral economics, and we need to sell this idea of the behavioral economic experiment. So I came up with the idea of, well, let's pay them. Let's see if they get it correct more if we pay them. So will people actually, if we pay them money, will people actually work harder to figure out the phase? I mean, this is a cognitively, relatively difficult task, cognitively. If we pay them per question, will that actually increase their effort? Now that's a really interesting economic question from this point on. So, so we can actually collect some data that's interesting from a psychology perspective. If you want to collect some political data on this, from a political perspective. So we might have a couple articles in this. Now, paying them. It's a small agency, so it gives very little money, though it's easy to get for early researchers. And John and I both got our PhD very recently. So we're eligible for the money. It's not too much. We can only get $2,500. Now we're going to run this in Hungary, where you have to pay people less, but you still have to pay people. So per phase, we want to give a big enough chunk of money that it actually looks like it matters. Because even per phase, I mean, in the end, when they do all the phases, they'll be able to collect a significant chunk of money. But even per phase, that chunk of money needs to be an incentive to make a difference from an economic perspective. So we were thinking something, like in the US, we would do at least $1 per phase. Now we have 38 phases. And we only have $2,500. So you can calculate the sample size we're going to have to deal with. So I'm starting to think that missing by design is not a bad idea in this situation. So we can actually see if we can have an IRT model, high response theory model, calculated to maximum likelihood. It's one of those procedures that is unbiased. You can actually it produces unbiased results. Now, so maybe do 6 and 6, 6 fade, 6 unfade, and maybe 8 and 8. So we can actually decrease the amount of money we'll have to spend. And hope it works. And this gets me to my first warning. If you do something like this, make sure you know what you're doing. And what I would recommend is you pre-test your design. You draw up the results that you expect, just like you would in a power analysis. You simulate a population. You sample from that population. The sample will actually have everybody's values. It's like a pseudo population. It's all simulated. The sample will have everybody's values. Delete all the ones you would delete in your design. So I would get 38 responses for all of these spaces from the people, and I would delete all of them but 6 and 6 randomly. And then I would analyze this pseudo data set to see if it runs. It's a really good idea to do that. I've gotten into trouble with this before. I have other people in the room who've gotten into trouble with this before. So you really want to pre-test. If you're doing missing by design, you want to make sure that you're not deleting too much data and your models will actually converge. It's just like doing a power analysis. One of the ways to do a power analysis is to do simulation. You create a lot of samples based on your expectations. You analyze all of them, and then because you know what the results should be, you check how many times have you gotten that result. That's a power analysis. Or that's a new way of doing a power analysis in the simulation. Do the same thing. If you have a plan missing design, always do this. It's not that hard. There's a learning curve, but it's not that hard. And plus has wonderful features that will help you do this. So there's a whole simulation engine built in. Okay. Yeah, so sorry, I should have skipped. So basically, Monte Carlo simulation is you drop the expected results. Again, you simulate the imaginary population, you sample from it, you create the missing data that you would create otherwise, you analyze, then you repeat. You do this a couple hundred times. And when non-convergence gotten down to a low level, let's say, something that's a risk you're willing to bear, then you do your analysis. But then you settle on your design, but not before. There's no miracles. So missing by design often doesn't work because there's too much missing data. So you should know what to expect when you start collecting this. And this is the hardest part of missing by design, because people got very prominent researchers, top scholars in the missing data field have gotten in trouble with this. So I know examples of that. Okay, any questions on this?
It's not that dire. It can work.
It can work, but you should know. You're the one who told me one of the examples that
Yeah, but we fixed it.
yeah, you fixed it. Yeah, how? I don't think it's a good solution.
You don't think it's a good
No,
solution?
now that I think about it, well, what they did was they collected data from, correct me if it's wrong, but collected data from children, or was it children?
No, we had adults.
Adults. Well, they collected a third of the data from they cut up the sample into 3, and they asked
No,
a
no,
third.
no.
No? And maybe we're talking about something different.
Well, go ahead, go ahead.
How'd you, like they cut up the sample into 3, and the third of the question was collected from one group, the third of the question was collected from another group, and the third of the question was collected from the third group, and the model just wouldn't run. So what they ended up doing is they went back and collected all the data from another chunky group, from another group. So they actually exposed one group to the whole survey, the whole length. Is that how it worked, or something similar?
It was not that basic, but we did have to get complete data from a small subset to get the
Yeah.
model to start. But
And I think I figured out how to overcome that completely now. So if you want to hear about that, I'll let you know. It involves several more versions of the questionnaire. There's several versions. But if it's computer assisted, you can do it easily. But
we actually had 21 scales that each was randomized for each person for almost 5,000 people. So it was, we didn't have 3 versions, we had 21 times as many possibilities. So it was much more complex.
oh, okay.
And so that way we could have interactions too. So it wasn't, we didn't even know how many versions we had, because it was each person for each scale was randomized to 2/3 of each scale.
Yeah. Okay.
But if you had no case with complete data, a lot of the multiple imputation software won't start.
Yeah.
It needs to have like 5 cases that have complete data. And it was only a difference of about 5 minutes on the survey, so we did about 300 out of 5,000 that had complete surveys to get starting values.
Oh, so you need it for starting values.
Well, we think that's why it didn't start.
Yeah. I guess that's not a bad solution then. Did you include those people who had complete cases in the analysis?
We just finished collecting all the data, so we haven't started the analysis yet.
I would exclude all the people who collected the whole data. Then I would use them for starting values, nothing else.
Why?
Because they're going to be faced with a higher measurement error because of survey fatigue.
But it could also be lower because they got more items for each scale. So you could test that, right? You could test that effect.
I'd have to think about it, it's testing. But yeah, so anyway, you need to try. I mean, that was one of the cases that I heard that somebody ran into trouble. So the best way to overcome that is to try it before you collect the data, simulate out something and see how it works. Okay, so let me give you my other example when I got into trouble with this. I was in Bob Belly's survey psychology class, and we're talking about context effects. Now, if you ask multiple questions on the same thing, you're prone to this thing called context effect, that your answer to the previous one will actually influence your answer to the second one. Can you help me with a good example, maybe? I'm asking to survey people over here.
Whether you exercise more and then asking about whether you want to exercise more. So how much you exercise and asking about whether or not
Yeah.
you intend to exercise more.
Okay, so how much you exercise and do you intend to exercise more? Yeah, so your first, depending on what order you're asking me, your first question might influence your second question, et cetera, et cetera. So I said, well, that's easy. Why don't you just do a planned missing design? Ask one question from half of the sample, ask the other question from the other half of the sample, and analyze it as planned missing. Sure enough, I thought it would work. So, the law of the hammer, of applying the law of the hammer, because since I know missing data problems, I see missing data problems everywhere, and I want to solve everything with missing data problems. But this is one of those situations that I actually thought it was a missing data, or it could be a missing data problem, it could be solved that way. So, again, ask half the sample one question, ask half of the sample another question, and randomize that to it's missing completely at random, and it should work, but it doesn't, because I wanted to run this instructional equation model, and when it got to calculating the covariance between those two variables, there was none. You cannot calculate the covariance of, well, you have data over here, you have data over here, and it just wouldn't calculate. It just didn't work. The model was under-identified because I had no information, no overlap. And I think that's where your convergence problems came from. There was zero overlap between some of these variables. So what did I do? I emailed Arbuckle to see if I can use Amos and a Bayesian estimator instead of a maximum likelihood estimator that doesn't use a covariance matrix. And he objected that he doesn't think that these models should be run. Well, and what I was interested in is would these models work? So it was not good enough for me, so I teamed up with somebody out in San Diego who I met at a workshop, and I know he does a lot of Bayesian models. And I just asked him to program the model and run the simulation. I simulated the data for him. I just asked him to program it into Winbugs, which does Bayesian, and run it through there. And sure enough, it worked perfectly. He produced unbiased estimates wonderfully. So just use a Bayesian estimator, and it'll work. So yeah, that's how we solved it, and I just took this paper to conference, and it works. And this is the model. We had we had a dependent variable. We had an attitude with 3 indicators that was prone to context effect. So each person was only asked one of these. The rest of them were missing. And again, it didn't work with regular maximum likelihood methods, but it did work with Bayesian methods. Any questions? Okay, now, I was faced with a very, very interesting problem once. One of my professors said that I wanted to research on African Americans, and I have a huge problem. I have the General Social Science Survey, which has an African American sample that asks one question, and I have the National Election Studies, which doesn't have it. It has a representative sample of African Americans in there that asks another question. Both samples had a random sample of African Americans, but we did not have the same 2 questions in the same data set. So, what do you think? Can we assume that data is missing completely at random? I think so. 2 random samples of African Americans collected around the same time. That gets you into trouble if it's not collected around the same time. Take the responses from one survey, one question, take the responses from the other survey, from the other survey, impute the rest. This is where we had 81% missing information. I said we need to make 50 imputations. This is also the thing that the imputed for 2 hours for one imputation. But it worked. And the results were actually wonderful. The results were as expected, perfectly working out and everything. So Okay, now there's another warning that these approaches are really considered crazy by most people. So if you're going to use any kind of missing data approach, be sure that your reviewer really understands what you're doing and really understands what are the downsides of not doing this. If you're trying to get something published, because oftentimes you get back, why did you do all these things? Why didn't you just drop those people? Because somebody, you get a reviewer that's never seen a missing data treatment, an appropriate one, and doesn't understand that whatever you do with missing data, you're treating it. And it might not be the best way to do it. If you just use the software defaults, that might not be the best way to do it. So the final solution is always what gets you published. So if you have to use a method that you don't think is the best, but your reviewer does, then maybe you need to make some compromises. I personally try to go with what I think is the best and try to explain in the manuscript that it is the best because of this and this and this, and it is better than these alternatives because of this and this and this. And you need to really spend time. I know you don't have too much space in articles, but you really have to spend the time to explain these, because most people do not understand missing data problems, do not understand the solutions to missing data problems, do not understand that the default solution doesn't always work the best. So these approaches are really, really considered crazy, especially when you start doing things like merging data sets and making plant missing data and crazy stuff like that. You really have to pray that you get a reviewer who's open to these new things. Now, one of the things that on the context effect article, we're actually scrapping it because we know that there's not going to be a single survey research journal that will actually eat this up. They don't think we're crazy. So I talked to a lot of people at the conference, and they all said, except for one very prominent statistician, they all said that we're crazy. And so they're actually going to scrap that project for a while, for now. Go ahead.
One thing on, I suppose approaches are a crazy idea. As you know, I'm an economist by training, and behavioral economist, training myself to be a behavioral economist the last 10, 12 years. And as a result, I've hung out at colleges like this that you're in, and I've tried to read the literature and try to understand how they come up with these scales they use, and I've tried to use all these psychological scales. And notoriously long, cumbersome to me as an economist, when he's over his races, like, well, cut this down. Why do you need 30 items in a scale? Okay, so what I've been doing over the years is I've been taking these scales out of the psychology literature and I've been cutting them down. Like a 30-item scale, I'm typically cut it down to 8 to 10 items. So this is the most reasonable items based on my theoretical judgment of the population I'm studying and what they probably will respond to. So to me, there's a big trade-off here. And then of course, I get critique. Reviewers say, well, you've taken reliability on the scale, you're down to 10 items, and you chose them, and you don't know if they're reliable or not, which well. So there's a trade-off here between the missing, and I'm considering going with the missing data approach now.
This is not even a bad idea. I know your situation.
See, what the problem is, missing data approach is going to give me more items in each scale, but there's a trade-off here, it seems to me. Why not just go with, what's the trade-off between reliability idea, only using 10 items in a 30-point scale versus using, half the items for 30, for example, and half, you know what I'm saying? I mean, some way to think about the trade-off between reliability and the missing data problems.
Well, the trade-off for you is that you are losing power. If you do a plan missing design, you're losing power to estimate that psychological trait from those items. You're definitely
scale down.
No. When you're using plan missing, you're losing power. If you're cutting the scale down, you're risking introduction of bias. You're biasing the scales based on which items selected, which items don't select. Once again, it's really, you find a reviewer that's going to be sympathetic to this idea that, hey, I sacrifice some power so I don't get bias? Or will you get a reviewer that's going to kill you for cutting down the items? That's what it boils down to. I believe that if you think it's, especially if it's just a control variable, I believe that sacrificing power it might be a good solution. But I don't like bias. I'd rather give up power and risk not finding something that should be there than the other way around, and introducing bias and finding something that shouldn't be there. So, I mean, that's the way I see it. On the other hand, if you don't have significant results, you don't get published. And if your reviewer doesn't like these crazy methods, then you don't get published. So I mean, you don't have to convince me. I believe that missing data techniques work, but then again, I mean, I've seen reviewers who it was like a 4-point ordinal scale. They used an ordered probit analysis, and one reviewer said, "Why are you doing all these crazy things? Why not just run OLS?" And they were like, "Because you shouldn't, because you have a continuous dependent variable. That's why." And I mean, this happens all the time. I don't know if it happens in economics and political science. It happens all the time. There are some reviewers who learned these methods in the 60s and haven't moved on since. And they're also refereeing journalists. And maybe back in the 60s that was the approach. They were just ignoring the assumptions. But so, I mean, you don't have to convince me. That's the bottom line. You have to convince someone else. I will never be your reviewer in the journal just because I graduated from this school and took your classes. So, okay. If you use multiple missing data techniques, or if you use list isolation plus imputation plus maximum likelihood, if you use multiple techniques, they all produce the same result. That's the best thing you can do. If you want to put in the work and do multiple techniques, and you actually find the same results, that is great. But then you can put that in the footnote and you cover it yourself. So it might be actually worth your time to do that. Okay, now, go ahead.
What if they don't? You know, we have 5 clocks and they all give you a different time. Which one do you pick?
Well, you want the appropriate answer or the honest answer? Well, you pick the one you like. No, I really think that if they don't produce the same results, you either pick the one that you think produced the best result.
The one you trust the most?
The one you trust most. And I would say you should be analytically driven, not theory driven in what you believe you trust the most. Because when you're theory driven in what you believe you trust the most, then you might be looking for something a little too hard.
Well, it also could be informative. I'm thinking about a specific example I've already consulted you on, but you know, we had 600 cases, and because of one variable, a list-wise deletion brought us to 461. So we lost a third.
Yeah.
And so with multiple imputation, when we brought them back in, it changed the results, but I think it's because those 200 cases were systematically different.
Yeah.
So I was violating the assumption of multiple imputation by I wasn't missing completely at random.
Well, multiple imputation only is missing at random. So if your other variables can actually predict the missingness, then
They should have been okay.
Then you should have been okay.
But I mean, I think it also could have, those 200 cases could have brought in some
Yes.
different, you know, sort of some meaningfully different information, and,
Yeah.
and comparing those models, and it could be more than technical.
And what's the variable you had missing on one of your variables of interest? Was that
Yes,
where
it
it
was
changed
our
results?
the focal variable.
Yeah. And is that where the result changed?
No.
No? I would actually go ahead and try vertical deletion.
You mean the size?
No, vertical. Throw out the variable. Throw out the variable and run the model again.
Okay.
See what happens then. But that might give you some information. And I mean, do you really theoretically need to have that variable in your model?
Yeah.
It's a question, but you do. It's the main variable of interest. So But then again, you have other problems too, as a small sample size. So that is a problem, and it's a multi-level problem too. Not correcting for multi-level is also an issue. So if you don't have the same results, then it's your judgment call. I would say use the result that was produced by the method you trust the most. And you might want to footnote that there's another method that you trust less for reasons following. You actually got a different result, so it should be considered as a plausible possibility that there might be something there, but use very weak language that, okay, you actually found this too, there's a different method, you don't trust this method as much, but there might be something there. And I might actually go ahead and do that. The problem is, you know how reviewers are supposed to be trying to publish stuff. So, okay, any other questions? So, okay, so I want to throw something at you that came up in a workshop I attended earlier this year. You know, when you create missing data by design, that's pretty radical. You don't have the right data, so you merge data sets. That's radical too. I mean, the response to that could be, why don't you get the money and collect the data, the appropriate data? But what if the problem is given? You can't overcome it. There's absolutely no solution to the problem, and they've been fighting with this problem forever. And I came across one of these situations, and then we were looking at fMRI imaging of the brain activity, functional magnetic resonance imaging of the brain. And one of the problems they face is that at any given time, they can only look at a slice of your brain. They cannot look at the whole thing. Now, this was event-related data, so they were showing people something, and they were looking at how their brain activity changes. And so time is a very sensitive thing. Like when they see what they're showing to them, how things light up in the brain is sort of an important issue. Now, at any given time, the fMRI can only take a look at a slice. And it takes from 1 to 2 seconds to take a picture of the whole brain, take pictures of the whole brain. So all these fMRI researchers were like thinking about how they can like combine those slices at one time point per second or one time point per 2 seconds to try to figure out what the brain looked like on average at that second. And there's all sorts of research going into this, and I'm sitting in the room thinking, why? Why not just take that one slice you have, cut it up for as many readings you have, and treat the rest as missing data? So I kind of threw it out there, and I actually was very happy to get the response, oh, that's interesting. So there were all these researchers. I mean, this is about as messed up data you can get. So I don't know who works with fMRI data, but I think they're really smart. I mean, you have three-dimensional dependence. But you know, one of the things you have to assume when you're running regression is your cases are independent. You have three-dimensional dependence in this data. Because what happens over here in the brain will depend on from what happens over here, over here, over here, over here. So to model that is crazy. There's also over 1 million pieces of information, variables per second, I believe, if you use the current per second or 2 seconds, if you use the current methods. And there's 50 people. How do you deal with 1 million variables and 50 people, and sample size of 50? So this is very, very messy data. So I admire everybody who tries to do something with this. But this was one of those missing data problems that I encountered. And that seemed like, well, it's a good idea to throw it out here because they're not going to solve their problem any other way, at least not in the near future. Maybe they'll come up with machines that can do readings faster, but not anytime soon. Okay, and the last thing I want to talk about is something I actually don't know much about. But it was a topic that is related to a missing data problem that I found very, very interesting, and it's something that hopefully I'll be doing research on in the near future. Now, causal analysis is a missing data problem, basically. Now, the difference between experimental and quasi-experimental design is the following. In an experimental design, you take your sample, let's say you cut it in half, let's take an easy one. You cut it in half. You do some sort of treatment to one group, you don't do that treatment to the other group, then you measure what effect the treatment had, then you measure what effect the treatment didn't have, so you can actually measure if the treatment caused the outcome in an experimental design. And when you're using a quasi-experimental design, observation study, you really cannot do this. You don't know if that lung cancer happened because of smoking. And that's kind of something that you don't want to do experiments on either. So your options are really limited. So what you can, one of the things that some researchers, and this is basically Joe Schaefer talked about for an hour in his workshop, started to think about is treating this as a missing data problem. Now, you can think about, for any person, let's say any smoker, you have an outcome. Did they get lung cancer in the next 5 years, or did they not get lung cancer in the next 5 years? You do not have data what would have happened to that person if that person was not a smoker. That data is missing. So it can be a missing data problem. Okay. I guess I'm getting ahead of myself. Okay, so this is just a growing field, and it's kind of cutting-edge research in missing data, and hopefully I'll get to it. It's based on propensity scoring and weighting methods. So the solutions to this so far have not been the imputation methods and the direct estimation methods I talked about. They were the weighting methods that's used for unit gun response that I didn't talk about too much today. I was asked not to, but there are a lot of people on campus who actually know that stuff really, really well. In the statistics department, I believe, and in SRAM also, there are some people who do sample weighting, and the missing data problems can be solved with sample weighting. And it is these weighting methods that they use to figure out how to deal with these causal models. But the idea is if you can isolate the causal direction, you're ahead of the game. Because right now, these observation studies, we can only assume causation. We can never test it. We can only see if there's an association between two variables. Now these missing data techniques will actually produce better matching. One of the solutions to this is to match up your samples. Try to match them up as best as possible. Take your observations and try to match up the people who are really similar on every other variable that you think could be related to what you're studying. Match them up as closely as possible, and then compare them. But treating it as missing data has already produced better matching techniques. And it's very interesting. I watched a speech of Don Rubin once, who is one of the consultants on the tobacco death case. And he said that they had to build a model. And he said, I want to build a model without seeing the dependent variable. He said, I will match everybody up for you without seeing the dependent variable through appropriate scoring methods, so I cannot tweak with the data. And they said that they had to go through a lot of legal processes of what variables should be included and excluded. So he said the results would be crap anyway, because it was the jury who decided what should be in the model and what shouldn't be, and they had no idea about anything. But to produce good, solid matching, they were able to do it without looking at the dependent variable. So this was a legally sound solution that was accepted by both sides. So there was no statistical tweaking, or there was no playing around with the data, or no include this variable for that variable, etc. to get a certain result. This was about as unbiased as possible. So it's important in this area also. And if you want to know more about it, you should look at the propensity scoring literature that's getting bigger. There was a conference last year in Vienna, in Germany. It was all in English, and they put all the speeches online. They put all the presentations online, including this Don Rubin presentation. I was just at their website. And if you're interested in this area of research and how missing data is used, or just the causal analysis, just email me and I'll send you questions, you want to talk about something, now would be the best time to do it. Go ahead.
Some workshops tomorrow, you'll actually show us how to.
Yeah, I'll show you how to do multiple imputation. I will use Amelia for imputing, because I think it's a really good software that's really flexible in terms of distributions. And I will use Norm for combining the results, and you can use whatever software you like for running the analysis, if you're running the regression. I will be using SPSS.
And speaking of tomorrow, we're having some computer software issues, so I will send you all an email this afternoon letting you know the final destination on where we will be. And I originally said we could end like, so I'll have a sign up, and if we aren't in Henslick, I'll put a sign up there letting you know where to go if you don't get my email by any chance.
Okay, and then in the second session,